Hey everyone, welcome back. In today's video, we will solve some important previous year GATE questions on linear algebra. These questions will cover topics like change of basis, linear transformation, rank and nullity. If my videos are helping you understand these concepts, please give them a thumbs up, subscribe to the channel and share with others who might benefit. So let's get started. Here is question LA18 on your screen. So it is saying that let T is a linear transformation from R3 to R3, given as T of XYZ is this. Then matrix of linear transformation T with respect to this ordered basis. So we need to find the matrix corresponding to the linear transformation T with respect to these ordered bases, not the standard I hat, J hat, K hat. All right, so we have already seen a question similar to this in our previous lecture where we were moving from R3 to R2, right? And we were given two basis set, one for the input vector space R3 and one for the output vector space R2. So this is that question, right? Here we were moving from R3 to R2. R3 is the input vector space and R2 is the output vector space. And because the input vector space and output vector space dimensions are different, so therefore we were given two basis set, one for the input vector space, this one, and this is the output vector space for the output vector space. But in this case, both the dimension of both input and output vector space is same because we are moving from R3 to R3, right? We are moving from R3 to R3. So that's why they have given us the same ordered basis for both input vector space and output vector space. So uh, this is the input vector space, right? This is the into input vector space. Let us suppose V is the vector belonging to the input vector space. So it has three dimensions. It belongs to R3, right? And this is the output vector space. And let us suppose T times V, the transform vector V belong to the output vector space. So it also belong to R3, right? So let us suppose A is the matrix corresponding to the linear transformation T, then A basically belongs to R3 cross 3, right? Because we are moving a vector from R3 to R3. So the input vector has three dimension and the output vector also has three dimension. So A would be something like this. It's a square matrix. Okay, it's a square matrix with three column vector. With three column vector. So this is the first column vector, this is the second column vector, and this is the third column vector. So all we need to find is where the first basis vector landed. So this is where first basis vector land, right? Where first basis vector land, where the first basis vector landed. Similarly, this is where the second basis vector landed. This is where the third basis vector landed. And this is the basis set. This is the first basis vector, this is the second basis vector, and this is the third basis vector. So let's apply the transformation to all these basis vectors. So our first basis vector is 0, 1, 0. So we will apply the transformation, right? Because we are moving from input vector space to output vector space, and this transformation is given by this T. This is the transformation, right? This is the transformation. So any vector belonging to the input vector space V will get transformed using this transformation T, and we will get T times V, right? So this is T times V. So this is the first basis vector 0, 1, 0. So we will apply the transformation. The transformation is given as this x plus y minus z comma x plus y plus z comma y minus z. So if you apply this to 0, 1, 0, so let us suppose this will be 0 plus 1 minus 0 comma 0 plus 1 plus 0 comma 1 minus 0. So this will be 1 comma 1 comma 1, right? This will be 1 comma 1 comma 1. Similarly, uh, you will transform the second basis vector, which is 0, 0, 1. So when you transform the second basis vector using this transformation, you will get minus 1, minus 1, 1 comma minus 1. All right. Similarly, for the third basis vector, which is 1, 0, 0, 1, 0, 0. So you will get 1, 1, 0. All right. Now, if you remember my last video, I already told you that 90% of student will make mistake here. Why? They will simply say, okay, the columns of A are nothing but the transformed basis vector. So this is the first transformed basis vector. So the first column will be 1, 1, 1. This is the second transformed basis vector. So the second column is minus 1, 1 and minus 1. Similarly, the third column is 1, 1, 0. All right. But if you remember, if you have seen my last video where I explained in very detail that this is completely wrong. This is wrong. Why this is wrong? Because see, these transform basis vector 1 1 1 the minus 1 1 minus 1 1 1 0 are not according to this basis set. They are according to the standard basis set I hat, J hat, K hat. So if you remember that for the R3 vector space X, Y, and Z, we the standard basis set is I hat, J hat, K hat, right? The standard basis set is I hat, J hat, and K hat, right? But they didn't ask us according to the standard basis set I had, J had, K had. They said that we need to give the matrix representation of transformation T with respect to this ordered basis. So this ordered basis is getting used for both the input vector space and for the output vector space, right? Because this basis set is for the input vector space, that's why we transform this these basis vectors, the first one, the second one, and third one, using the transformation. We get this, but we need to further convert them according to this basis set. These vectors are not according to this basis set. These are according to standard I hat, J hat, K hat. We further need to convert them. So if you have seen my last video, I did the same thing here, right? Here this is the first this is our first basis vector b1 hat, b2 hat, and b3 hat, right? I transformed it and I got this, and then I wrote this 2 comma 0, this transform basis vector with respect to this basis set, which is the output output vector space basis set. But in the current question, both the basis set for input vector space and output vector space is exactly same. Okay, and here because it was pretty simple, because we need to write 2 comma 0 in terms of e1 hat and e2 hat, so these are two-dimensional vectors, so it was pretty simple that this will be 0 comma 2, because 2 comma 0 is nothing but 2 times e2 hat, so the contribution of e1 hat is 0 and the contribution of e2 hat is 2, so it was pretty simple. But when you come to this question, in case of three-dimensional vectors, it's not that much straightforward. So if I say that if you need to write 1 comma 1 comma 1, that is this transformed vector. So t times 0 comma so basically this is the first basic vector, right? T times 0 comma 1 comma 0 is 1 comma 1 comma 1. If I say write this 1 comma 1 comma 1 in terms of these basis vector, so what are our basis vectors? So the first basis vector is 0 1 0, the second basis vector is 0 0 1, and the third basis vector is 1 comma 0 comma 0. If I say that write them according to these basis vector, then it won't be that much straightforward. We cannot do a hit and tell, or it may take time. So another way is, because this vector need to be written as a linear combination of these three vectors, because these three vectors are linearly independent. That's why they are basis set. Any vector belonging to a basis set is a linearly independent vector with respect to other vectors in that basis set, and these three span the entire R3, right? So if these three are spanning the entire R3 and they belong to the basis set, then any vector v can be written as a linear combination of these three vectors, right? So I can say that any vector v, any vector v, any v is nothing but some alpha times b1 hat plus some beta times b2 hat plus some gamma times b3 hat. This is true, right? That's why b1 hat, b2 hat, b3 hat are basis vectors, right? Similarly, if we take this I hat, j hat, k hat, we say that any vector v is nothing but alpha times I hat plus beta times j hat plus gamma times k hat, right? Similarly, we have replaced I hat, j hat, k hat with our new basis vectors b1 hat, b2 hat, b3 hat. So any vector is nothing but a linear combination of these three basis vectors. So similarly, this 1 1 1 is a linear combination of our three basis vectors. So it is alpha times b1 hat plus beta times b2 hat plus gamma times b3 hat, right? So what is b1 hat? B1 hat is 0 1 0, 0 1 0 plus beta times b2 hat is 0 0 1 plus gamma times b3 hat is 1 0 0, right? So and this is equal to what? This is equal to 1 comma 1 comma 1, right? Now you can simply if you expand this, this will become gamma, because alpha times 0 is 0, beta times 0 is 0, gamma times 1. So if you add, you get gamma, alpha, beta, and here you have 1 comma 1 comma 1, right? So you will simply get alpha equal to 1, beta equal to 1, and gamma equal to 1. So basically this is the this will be 1 1 1. So the first vector, so the this sorry not the first vector, the this one, you take the first basis vector, you transformed it using this linear transformation, you get this 1 comma 1 comma 1, and then you wrote this transformed basis vector 1 comma 1 comma 1 with respect to the basis set, with respect to the original basis set. So you get this vector. In this case, it's by coincidence that these are same, but it's not always. So for the matrix A, the first column is 1 1 1, that is this. So this is the second column vector, that is 1 minus 1 minus 1. Okay, so the second column vector of your matrix is 1 minus 1 minus 1. Similarly, you will do for the third basis vector. So that is 1 comma 0 comma 0. So again, this is alpha times 0 comma 1 comma 0 plus beta times 0 comma 0 comma 1 plus gamma times 1 comma 0 comma 0. And this we already calculated. This is 1 0 0. This is 1 1 0. All right. So 1 1 0, and we will get again gamma, alpha, beta, and in this case alpha is 1, beta is 0, and gamma is 1. So this is our third column vector, that is 1 0 1. So 1 0 1. All right. So this is the correct matrix representation with respect to the given ordered basis. With respect to the given ordered basis. So if they have said that this basis set B is only for the input vector space, and for the output vector space the basis set is I hat, J hat, K hat, then in that case this would be the right answer. But because this is the basis set for both input vector space and output vector space, so we need to further transform. Okay, we further transform it. So the process is straightforward, just like we did in the last question in the previous lecture. You need to first transform the basis vector according to the given transformation. Okay, once you transformed it, you get this, and now you need to write these vectors according to these basis vector, and this is the process for that. Okay, and this is the correct matrix. Let's see question LA19. So we are given a transformation T which is from P3 to P3, where P3 is a third degree polynomial. Okay, so P3 is a third degree polynomial, that is, it is of type A plus Bx plus Cx square plus Dx cube, right? So we are given this transformation, which is T. Transformation T is T of P of x is integration 1 to x, first derivative of the polynomial at a point t dt. All right, we need to find the matrix representation related to the standard basis. So this is the standard basis. So we know any 3-degree polynomial is nothing but a linear combination of 1 x, x square, and x cube, right? So this is 1, basically this is 1 x, x square, and x cube. So any 3-degree polynomial is nothing but a linear combination of these four terms, a 1 x, x square, and x cube. So these are the standard basis for P3. So the standard basis for P3 contains 1 x, x square, and x cube. We have seen this many times in the previous videos, where I solved questions similar to these 2-degree, 3-degree polynomial. Okay, so we need to find the matrix representation. As I already told you, so this is a P3 to P3 transformation, right? So what is the let us suppose A is the matrix representation for T. So it belongs to R, 4 cross 4. Now you may be saying why 4 cross 4? It is a transformation from P3 to P3. Yes, it is a transformation from P3 to P3, but P3 contains 4 terms, right? Because a 3-degree polynomial can contain at max 4 terms because there is a constant also, x to the power 0, x to the power 1, 2, 3. So that's why A belongs to R 4 cross 4. So there are 4 column vectors in A. And we already know that column vectors of a matrix is nothing but where the basis vector land after transformation, right? So this we have seen in the previous question as well. So there will be 4 column vectors where the first column vector represent where the first basis vector land after applying the transformation T. So what is the first basis vector? 1. What is the second basis vector? X, and so on and so forth. So what is this? This is nothing but T times 1. Basically, where the first basis vector land after applying transformation T. This is T of x. This is T of x square, and this is T of x cube, right? So all we need to find is the transformed basis vectors. That's all. So let us suppose we first find T of 1. So we are given T of P of x, which is 1 x, the first derivative of this term. So because it is a constant, so first derivative is 0 into dt. So this is 0. So how we can write 0 as a linear combination of these 4 terms? It is nothing, it just multiply everything with 0, 0 into 1 plus 0 into x plus 0 into x square plus 0 into x cube, right? That is how we get 0. So basically, this is nothing but 0, 0, 0, 0, right? Similarly, we will find the transformation of the second basis element, which is x. So in this case, the first derivative of x is 1, 1 times dt, and then you take the integral of 1. The integration of 1 is nothing but x itself, and sorry, uh, because this is dt, so t, t, and then you put x and 1, so this become x minus 1, right? How you can write x minus 1 as a linear combination of these? It's pretty simple. You take minus 1 times the first basis vector, which is 1, plus 1 times the second basis vector because we need x, plus 0 times the third basis vector, plus 0 times the fourth basis vector. And that's how you will get x minus 1, right? So this vector will become minus 1, 1, 0, 0. That's all. Similarly, you will do for x square and x cube. So yeah, so this is tx square and this is tx cube. So we have calculated the transform all the transform basis vectors. So this is the first transform basis vector, this is the second, and this is the third and fourth. So A is nothing but we just uh, the columns of A is nothing but these transform basis vector, that is 0, 0, 0, 0, minus 1, 1, 0, 0, minus 1, 0, 1, 0, and minus 1, 0, 0, 1. All right. So what was asked in the question? So they are saying that if okay, it is given that this is M. All right. So it is given that this is not a, this is M. All right. This is M. So the matrix representation is M. So we need to find M plus M transpose. So it's pretty simple. You know M, then you can find M plus M transpose. You just transform this matrix and then add both the matrix. So take it as a homework. All right. So let's see LA question 20. So we are given a linear transformation T. So this is a transformation from R2 to R3. So that is we are moving from the two-dimensional XY plane. So this transformation is taking from us from two-dimensional XY plane to this three-dimensional XYZ volume. Okay, so we are moving from one dimension to from 2D to 3D. Okay, so it is defined by, so this transformation defined as this x1 x2, is equal to x1 comma x1 plus x2 comma x2. So because the input vectors are coming from R2, so that's why transformation T is moving a vector V belonging to V, which is an input vector belong to R2, and this is T times V, which is the transformed vector. The output vector belongs to R3. All right. So then we need to find the nullity of T. So to find the nullity of T, we first need to find the matrix representation of T. So let us suppose a matrix representation of linear transformation T is A. So we know that A belongs to R3 cross 2. Why? Because the input vector space is R2, so this represents the dimension of the input vector space, basically the dimension of the input vector, and this represents the dimension of the output vector. And so this matrix basically contains two column vectors, right? This contains two column vectors, where the first column vector is where the first basis vector land, and the second column vector is where the second basis vector land. Now, because in this question we are not given any basis set, because in this question there is no basis set at all, right? So we can take the standard basis set. So we know the standard basis set for R2 is I hat J hat, right? It is I hat and J hat. So all we need to find is, so the first column vector is where I had landed, where I had landed. That is T times T of I hat, not T times. And this is where J had landed, where J had landed, right? That is T of J hat, right? We need to find this. So we need to find T of I hat, that is the transformed of I hat, the first basis vector. So what is I hat? I hat is 1 comma 0. We can use this formula. The transformation given as T x1 and x2 is this. So this will be 1 comma 1 comma 0, right? And T of j hat. T of j hat is what is j hat? 0 comma 1. So this will be 0 comma 1 comma 1. So these are the two transform vectors. Now if you see the first question, in the first question, after applying the transformation, we further need to uh, write this transform vector according to the ordered basis, which is this, right? Because this ordered basis is both for input and output vector space. So even after doing the transformation, we further need one more step where we write this transformed basis vector in terms of the basis set. But here in this question there is no basis set given for input vector space or output vector space. So just like we assume the standard basis for input vector space, that is I hat and j hat, the same we can assume for the output basis output vector space. That is the basis set for output vector space is the standard set, that is I hat, j hat and k hat, the standard set for uh, R3 vector space, right? So we know we don't need any further conversion. So the matrix representation A of T is nothing but where the first column vector is the T of I hat, that is 1 1 0, and the second column vector is T of J hat, that is 0 1 1. Now we need to find the nullity. So before that we find the rank. So rank is basically the number of linearly independent column vectors. So both of these column vectors are linearly independent. Therefore rank of A is 2, because there are only two column vectors and both are linearly independent. So rank of A is 2. And we know that rank of a matrix A plus nullity of that matrix A is equal to the dimension of the input vector space, and we are moving from R2 to R3, so it is n, right? For any matrix A m cross n, rank of A plus nullity of A is equal to n. That is the dimension of the input vector, right? So we know the rank of A is 2. We need to find the nullity of A, and we know n is 2 in this case because A is a 3 cross 2 matrix. The vectors are coming from R2, so the input vector space dimension is 2. So from here we can find that nullity of A is 0, and this is what asked in the question. All right. So that's all for this lecture. We covered three very important questions. These kind of solidify our concepts. Okay. So if you found this video helpful, then like and subscribe to the video and also share with other. So till then, bye. Thank you.